Hello and welcome! I am Spiky and this is part 2 of Fresnel. In this part I will tell you something about light and Fresnel. I will start with a quick reminder of part 1 in the form of some new pictures, and then I will try to teach you something about so-called quantum electrodynamics as far as it concerns Fresnel. But first, look at this simplified light simulation I have made for you. This is more or less what Fresnel tells us that happens. And here's what we get in cycles after only 6 bounces of light. I would like to emphasize here that I'm not trying to criticize cycles, or any path tracer for that matter, but I just want to make things better, and it only works if you can see your mistakes, unpleasant as it is to hear that you're wrong. In this next picture the light enters the room in a steeper angle and you can clearly see the Fresnel effect in action. And here's what we get with cycles. This time only showing 5 bounces, but you'll get the idea, I hope. Now try to imagine what these pictures would look like after 128 bounces, which is the default value for full global illumination in Blender, as you can see. Now hopefully you can understand that nothing would change in the way the light reflects if we move or rotate the camera. That was part 1 in a nutshell. Now comes part 2. What is light? Light consists of a bunch of very small particles called photons. Each of these photons can be characterized by 2 properties, energy and spin. Instead of spin you will also find the term polarization, but that's the same property and it's something I will completely leave out of this tutorial so as not to make it more complicated than necessary. The energy of a photon is also known as its frequency, color or wavelength, but again, these all describe the same characteristic. I suspect that you already know a few things about light, like for instance, light travels in straight lines, the speed of light in a vacuum is constant, and light reflects from a surface, if it reflects that is, in an angle opposite to the surface normal. If you didn't know this, don't worry, because all of those facts are wrong, as I will try to show you. So keep watching, this is going to be exciting. Here's one way to see the quantum theory of light. I got most of what I'm about to tell you from Nobel Prize winner Professor Feynman, so don't think that I'm crazy. It's the theory that's absurd, but as far as we know, rather accurate. It agrees with all the experiments so far. Almost everything that can happen in nature, if broken down to its basics, is that A photon can travel in a vacuum from one point to another, B, an electron can travel in a vacuum from one point to another, and C, an electron can absorb or emit a photon. Apart from gravity and radioactivity, that's all that happens. It just happens a lot. If we call each of these, when they occur, an event, we will just need to combine these events and we have the whole world explained. Now comes the crazy part. We will assign to each possible event a 2-dimensional arrow, which is called a probability amplitude by physicists, but I will stick to arrow. If we now create a unit arrow, for reference, we can describe each arrow by its length and its angle compared to the unit arrow. Because we want to combine events, we will need rules for combining arrows, and well, I will now give you those rules, so that you will be able to understand everything that ever happened. Rule number 1 is called adding 2 arrows, and it's done by putting one after the other. The tail of one arrow must be put at the head of the other. The resulting arrow is the blue one here. This we will use when there are different ways for an event to happen. We will draw an arrow for every possible way that the event can happen, and then add all the arrows for those possibilities. Rule number 2 is multiplying 2 arrows, and this is done by adding the 2 angles and multiplying the length. The result is the red. We will use this when 2 events happen one after another, or at the same time but independently. Now we will say that the arrows rotate anti-clockwise, which is just a convention, very fast. Something like 430 trillion times per second for red photons, and even more for blue light. So now we have yet another way to characterize different colors of light. 2 more things. If a photon reflects off a front surface, like from air to water for instance, we must rotate its arrow 180 degrees and shrink it by a factor, depending on the IORs. In the case above, where we go from air to water, we will have to divide its length by 7. If it reflects from the back surface of, for instance, a glass plate, we will not rotate it 180 degrees, just shrink it. If the two media are air and glass, for instance, we shall divide the length of the arrow by 5. Don't ask why, these are the rules. If you don't like them, you'll have to go and play another game. This means you'll have to find some parallel universe somehow where the rules are more to your liking. We cannot change the rules, that's what rules mean. You cannot change them. And finally, the probability that an event occurs is the square of the length of the corresponding arrow. That's it. See you next time. Or maybe I will show you some examples, so that you can see the beauty of this absurd set of rules. We will start very simple with a photon emitter, a light, L, a mirror, and a photon registration office, O. Let's say, for simplicity's sake, that L only emits red photons. What is the chance that a photon gets from L to O? To be able to calculate that, we must make an arrow for every possible way that this can happen. And there are many ways that this can happen. To be more precise, there are infinitely many ways that this can happen, so we appear to be in great trouble already. But let's just get started and see what happens. First, we draw some possible ways the photon can get from L to O. Yes, all of these are possible, and what's worse, they're all equally likely. I hope that it will be clear to you that the different colors are there for clarity and do not represent different colors of light. Because, like I already said, our light only ever emits red photons. This is called the monochromatic light, by the way. Now, we will draw the accompanying arrows which, because all possibilities have equal chance to happen, all have the same length. But because some paths are longer than others, they do have different angles. If a path is longer, the time it takes a photon to get from L to O is longer, so the arrow will have turned around more. I'm not doing anything quantitative here, this is just to show you the principle, and if you bear with me for a little longer, you will see something really beautiful happening. We now must add all the arrows. Now here's the magic. Most arrows just turn around in circles, and only the white ones, whose paths are of almost the same length, make an actual contribution to the final arrow. This is why light appears to travel in straight lines, and why it seems to reflect mirror-like. So, why did we even bother with all the other possibilities, if all that is left are the ones with the shortest path? That's what we expected anyway. Well, let's do something crazy now. We will move the mirror to the left. As you would probably expect, there are hardly any photons that reach O. But if we now remove some of the mirror at exactly the right places, which is known as grating, so that we have less mirror, part of the light can now pass through the glass of the mirror, something that you probably didn't expect happens. Suddenly, a lot of light reaches O. This cannot be if the light reflected mirror-like. Let's see what actually happened here. We took away the mirror at exactly those places where the arrows were pointing downwards, leaving us with something like this. If we add them, now our resulting arrow is huge. The scratches were exactly calculated for a red light and do not work for other colors, but if we rotate the mirror a little, it works for green light, or yellow, or blue. Just not for two different colors at the same time. And you've all seen this effect in action. If you shine a white light, it consists of all color, on a CD or DVD, which have lots of tiny little grooves, you can see all the colors of the rainbow and they move around when you tilt it, and now you know why. Now let's consider a glass plate in air, from which, as we know, the light is only partially reflected. We will make it a bit easier on ourselves by pretending that the light travels in straight lines and is reflected mirror-like. We now know that this is only an approximation, but it will serve its purpose in this case. The way the photon can get from L to O are in this approximation mainly given by a photon goes from L to F, reflects, and then goes back from F to O. Or a photon goes from L to B, reflects, and then goes from B to O. So we draw our arrows for the first way and combine them according to our rules. We multiply the arrows. Next, we draw our arrows for the second way and multiply those. Finally, because these are different possibilities for the photon to get from L to O, we will have to add the two resulting arrows to get our final arrow. If we now take the square of the length of the arrow, we will have the chance that a photon reaches O from L. In other words, how much of the light coming from L will be reflected from our glass plate. If you are very clever, you will already realize that this does not depend on how far the glass plate is from the light, because a photon will have to travel this distance anyway, whether it gets reflected from the front or the back surface of the glass plate. But it does depend on how thick the glass is. If the glass has zero thickness, there's no glass and therefore no reflection, as you would expect. But if we increase the thickness of the glass, the amount of reflection rises slowly until it reflects twice as much as you would expect, and then it goes down again, back to zero reflection. This then repeats itself. This repetition has been measured with glass thicknesses up to 50 centimeters at least, and that was in 1980, so probably even thicker now. As in the case of our glass in air, the chance that a photon reflects from the front surface is about 4%, and the chance that it reflects from the back surface is also 4%. But the sum of these lies between 0% and 16%, depending on the thickness of the glass. Now, don't get any foolish ideas in your head that this needs to be implemented in CG. Under Nergman circumstances, we do not see this effect because thicknesses for which the reflections is zero, for instance, are different for each wavelength, while for different colors the arrows rotate at different speeds, or frequencies if you prefer. Now, that was quite shocking, I think, so let's take a little break and go to the beach. The weather is nice, there are people swimming, there is a lifeguard, Louis, L for short, and the beautiful girl Olivia, O for short, drowning. The lifeguard, if he's any good, must try to get there as soon as possible. But how does he do that? The shortest possible way, lengthwise, would be in a straight line, but as swimming is slower than running, he can get there faster by spending less time in the water and more time on the beach. If he took the blue way, he would spend the least time in water. But there's an even faster way. White is the fastest way L can get to O. Where exactly he has to enter the water depends on how much slower he is in the water than on the beach. It does not depend on where any eventual spectator might stand on the beach or even in the water. Of course, no lifeguard in his right mind would waste time calculating where the best place is to enter the water, but it's important to know that such a place exists. Now, Fresnel was not a lifeguard, and there was no drowning girl in sight, so he decided to calculate where the best place to enter the water was, and he put his result in a nice set of formulas. He even put in how much slower the lifeguard could be in water, because not all lifeguards run and swim at the same speeds. And because he had enough time, he also put in a factor for the thickness of the water. He imagined that some water could be more like gel and other almost like a gas. He called this IOR, and how fast the lifeguard was he called wavelength, lambda. And now you know why light bends when it enters a material of a different IOR. There is of course a lot more to tell you, but I will end here with just a few remarks without really explaining them. People always say that light travels slower in glass, for instance, than in air. But what actually happens is that a photon in glass can be absorbed by an electron, and after some time the electron can emit a photon in another direction. This can happen many times. It is called scattering of light. And therefore the time it takes a photon to get through a layer of glass is on average longer than in air. There are less electrons. And, unimportant for us but fun to know, is that a photon in a vacuum has an amplitude to go slower or faster than the speed of light. But over relatively long distances compared to the size of an atom, these amplitudes will cancel out. But it's even more horrible. Every particle has an amplitude to travel backwards in time. This is then known as an antiparticle. And if a particle comes together with its antiparticle, they annihilate each other. Now you know what people are talking about when they're talking about antimatter. Well, that's all for now. Thanks for watching. I hope you enjoyed it. Leave your questions and comments below, and I hope that you will join me again in part 3, where we finally open Blender and start getting practical. For those of you who want to know more about quantum physics, I have put some links in the description. Bye!